So to 1:30 or less, or how long? Okay.
45 minutes.
Do I have to wear a microphone?
No.
Okay.
Hi everybody, it is a pleasure for me to introduce today's speaker, Professor Lee Harman. Lee got his PhD doctorate at the University of Michigan. Then he was a senior scientist at the CFA for almost 30 years. And then around 2005, he moved to the University of Michigan, where he is the Leo Goldberg Professor. Lee is a very well-known scientist in the field of star formation. He is mainly a theoretician, but with a very deep understanding of the observational things. His book on accretion processes in star formation is a reference book in the field, and Lee has participated in a number of panels. He was former vice president of the American Astronomical Society, and he has been the chair of in the last decadal survey of the panel on planet and star formation. So he knows very, very well the field, and today he will talk us about issues in star and cluster and planet formation.
Thank you, Guillaume. I'm not sure I'm going to get to the planet part, but I can do so, and I apologize in advance because I have a little jet lag, so if I fall over, please pick me up. Okay, I have actually a couple of topics, and I just thought that just as an introduction to this, I wanted to mention a student of mine that's working with Laurent Leonard on, as part of Laurent's project to measure distances to the nearest star-forming clouds. I mean, many of you know that this is an issue in star formation. Maybe Gaia will sort out everything. But for now, we would like to have accurate distances. And in this case, using the VLBA for non-thermal sources, and then using the VLBA to get the parallaxes. And so we're just mentioning that we're doing this, and my student, Marina Kunkel, is leading the study of the Orion molecular clouds. Why some of these stars emit non-thermally is not very clear. Just a small fraction do, and they come and go. There are a lot of things that don't have, young stars that don't have disks particularly, and also there's a high frequency of binaries for some reason. So there's some magnetic activity which gives you this gyrosynchrotron radiation that you can then measure. So this is kind of the result so far. Here's the Orion Nebula, and the Orion A cloud kind of extends through here. These are the individual distances and parsecs. So currently now we have measurements of going on a bigger scale. Here's the Orion Nebula region, Orion Nebula cluster. Here's L1641. And so some years ago, Carl Minton and his collaborators had gotten a distance of 414 parsecs, so we're reasonably consistent, but maybe a little closer. It's not clear whether this part is farther away because there's just one star there. But in any event, this is important for trying to get the luminosities of the stars, which then correlate or determine their ages, basically. So here's just some of the plots. Some of them are pretty bad, so we throw them out. Some of these guys are binary sources, and so we have to get more epochs in order to take out the binary orbit. So this is ongoing work, but I think we'll be done with it. We'll have a paper out in the summer with the first distances. Some of these things that seem like they're very discordant distances are because they're binaries, and we just haven't resolved the periods. Okay, so let me get to the main topic then, which is talking about the formation of star clusters. And this is work I've been doing with Javier Ballesteros in Morelia, Fabian Heitsch, and Andy Burkert now in Munich, and my recent student, Alexandra Kuznetsova. So you probably know that most stars form in clusters, and so the question is, why? And then I want to go on to talk about the cluster mass function. So there's a well-defined mass function for star clusters. And I think we can understand that, and even that suggests something about how high mass, what sets the initial mass function for high mass stars. And I should have put down the answer here so you could, take a nap, or if I fall asleep, you know the answer. The answer is gravity. So very simply, gravitational acceleration answers all these questions. At least that's what I'm going to claim. So, as you know, stars mostly form in clusters and groups. So here I just showed you the distances. Oops, this is kind of bright. To the Orion A cloud and Orion B cloud. These green things are Spitzer Space Telescope identified infrared sources, so they're young stars. Just looking at the Orion A cloud itself in more detail, this is the Orion Nebula cluster, which is elongated. The Orion Nebula sits in here. And then you have this very long sort of filamentary structure. And this is the big cluster, a couple thousand stars, but within that you can start to identify smaller groups, maybe of a dozen or 2 dozen stars. You might not call those clusters, but there's clearly a whole spectrum of clustering, from the large size to even small numbers of stars tend to cluster. So the first thing that we started thinking about with Andy Burkert is that in some of these regions it's quite clear that the clusters tend to be at the ends of an elongated cloud. So if I look at Orion here, so here there's Orion A cloud, Orion B cloud. So in this case, the Orion Nebula cluster is sort of over towards the end of this filamentary structure in molecular gas. And here's in Orion B, there are 2 clusters sort of at each end of that filamentary structure. And so the question is there some way of understanding that? Or does that give us a clue? And then also in NGC 2264, another young cluster. So here it's sort of elongated again, and there are clearly more concentrated groups, and the molecular gas runs this way. I don't have a map of the gas, but here's an extinction map, so where you don't see stars is extinction. So you see there's a cloud running through here, and the 2 lumps of stars are sort of near the ends of the cloud. Not perfectly, but not too bad. So what is the suggestion? And so what Andy and I had worked on was that it's just gravitational focusing from a system where you don't have spherical symmetry. And, other than in theory, you don't have any spherical systems. And as I showed you, a lot of these clouds are very elongated. So what happens? So how can we do that? So we did a toy model several years ago where we just took, actually just in 2 dimensions, and we just made we just took a sheet of gas, which originally was just elliptical, and for fun we added a little bit of bells and whistles. We put a density gradient, so this is a surface density plot. So it's a smooth density gradient, higher, more dense here, less dense here, and we made it rotate for some arbitrary thing. So this is where we start from something that has no particular structure other than it's elongated in this direction. And so you just let it go under gravity. It's just self-gravitating, has lots of Jeans masses, so it's just going to collapse. So as we let this go, you see we gets a little bit focused, and then it gets even more focused, and it makes these filaments along the edges, with kind of a big bunch of stuff here. And finally, we let it go some more, and then there's our ending stage, and that's a comparison with the 13CO map of Orion A. So we've made our filament. The Orion Nebula cluster is in here. This isn't very resolved, but that's the maximum of the mass. So most of the mass has been put in here. So just by the very slightest non-sphericity and gravity, you can go from something that has no filamentary structure, and you let it go, and you can make that. So there's a natural tendency under gravity to form condensed filamentary clusters as long as there's not too much turbulent motion, or if the thing was rotating too fast. What happens here is, because there's sort of at the end of this, that there's a gravitational focusing just because of the geometry and a little bit more of the mass. But basically, you concentrate all this stuff in here, because when you have some radius of curvature, and you don't have infinite clouds, you don't have spherical clouds, you have a little tight radius, it just is like the focus of an ellipse. And so you pile up a whole bunch of stuff here, and then, although the light is too much here, this then would be something where you could get the Orion Nebula, concentrate the gas so you could make a massive cluster there. And so this kind of picture then naturally forms. If you have an elongated cloud, you can, just by gravitational focusing in the non-spherical geometry, you can pile up stuff and make clusters. And you may have groups all along here, but the ends would be particularly appropriate for really focusing down and getting up the mass. So the idea is then, this is just gravity and starting with a non-spherical geometry. So this is the way that we can assemble a lot of gas in a small region, which then could make a cluster. So this was a really toy model, not very much resolution. And so more recently, with my student Alexandra Kuznetsova, decided, okay, let's not just make this a sheet. So we took a triaxial ellipsoid. The mass is sort of arbitrary, because this is isothermal at 10 degrees, so things scale. And the idea was to kind of put in some rotation, and so the idea was see if we could get something like this with a little bit more realistic simulation, although still pretty simple. So we don't have feedback from stars blowing out things, and we haven't put the magnetic fields in yet. So we're just letting it collapse under gravity, and then we have sync particles so that they're collapsed down into stars. And unlike the previous simulation, we said, okay, well, we need maybe there's some turbulence, so we put in some small-scale velocity fluctuations. These are initially supersonic, but because they're not continually driven, they dissipate pretty quickly. And all this does then is it makes density perturbations. Okay, so we have our cloud, and we've just put in something or other so we can get individual stars or sync particles. So this is what it does. This is now a simulation, and I'll stand in the light so you can see it a little better. So each of these little green guys is a sync that has formed, and so all that's happening is that basically the thing is collapsing gravitationally. There's small scale collapse to make stars or sync particles, and there's a little bit of rotation, so the whole thing's going up towards this end. Okay, so very, very simple simulation. And starting, as I said, from something that is elongated but apart from having a little bit of substructure, doesn't really do much of anything. So we end up making sort of an elongated cloud, and we'll end up with, because it's near the end here, we'll end up with our more massive star cluster at the top. Okay, so I don't think you can see this too well, but anyway, you saw the movie, and here at the end, we've got our filamentary. Thank you. I think it's a little easier. You don't really need to see me. I'm still whatever. So just out of that evolution, we ended up with a big star cluster down here, and then along here it's sort of a filament, and you have these little lumps of stars. And we didn't put that in particularly by hand. There was some random distribution of gravitating masses, but it was just random. And so all that happens here is that if you have an overdensity, gravity wants to make it even more overdense. And so you'll just end up with making little groups all along here. And then down at this end, where we've kind of, the end of the cloud, so to speak, there's a natural tendency to really focus the stuff in. And so we end up with our star cluster down here. So this isn't an attempt to reproduce Orion, okay? But it's just, and of course, then there are more complicated effects which we'll have to put in eventually with magnetic fields. There are high mass stars in here, which they would have feedback and blow out the gas and so on. But this just sort of illustrates how easy it is to clump stuff with gravity. And so without having to introduce some turbulent structure or anything else, you just naturally get this. So you can put in some other turbulence, you can make it more complicated, but as long as you've got gravity, and of course gravity is a long-range force, right? There's no anti-gravity that we know of, and so things just collect. Just as kind of an amusing thing here, I don't know how realistic this is. Again, it's not a very realistic simulation, but we thought, what happens to the massive sinks? So you may know that there's some evidence, or at least some argument, that the most massive stars have to form in the most dense regions in order to have enough mass, right? And what actually happens in this simulation is that the massive guys start out in some distributed fashion. So here's half a parsec distance for scale. And so they can accrete. They're accreting all the way through here, but they all kind of fall into this cluster. And so they grow a lot, but not necessarily right in the middle of the cluster. However, they do end up in the middle of the cluster because they're heavy. So in this case, we do see a mass segregation with most of the mass, with the higher mass guys in the center, but it didn't necessarily mean that they started forming there. Now, whether that actually works in reality is not quite so clear, because this is an SPH calculation. It doesn't have a lot of complicated physics in it, and so maybe there'd be something different. But I think there's a general possibility that the nature versus nurture argument about the high mass stars may be very difficult to discern, because even if you start out here, you can end up there, and this is a whole, this whole time scale is about one free fall time of the global cloud. So that whole sequence, all of these sequences that I've been showing you are about 1 million years when you scale it to something like Orion's mass, or 1,000 solar masses. So all this stuff happens in kind of like 1 million years or so. So it happens fast. Okay. Now, the mass function. So one of the interesting things that has come out of studies and clusters, somewhat in the Milky Way, but also in nearby galaxies, is trying to get mass functions for young star clusters. And this is a little bit tricky because you have to, basically you're assuming some mass to light ratio. But the Milky Way clusters show something like this. So they actually have a fairly well-defined power law mass spectrum. And it's such that if you do dn/dm, it's m to the minus 2 or m to the minus 1 in log space, which is what I'll use from now on. These are actually the fits with the errors from Rupali Chandar's study of clusters in M83, sorted by less than 10 million years, 10 to 100 million years, and then somewhat older, but still not that old clusters. So I've just tried to sell you on the idea that just gravitational contraction, focusing in some kind of geometry or whatever, is responsible for making clusters. Well, can it then also reproduce this mass spectrum? If gravity is what's involved in assembling the gas and stars, maybe it should be able to explain this power law. So, there's a very old paper by Hans Sinneker, which was mostly aimed at the stellar initial mass function, the high mass n. And so what he showed was that if the accretion rate for a given object scales as the square of the mass, so you have some kind of medium that you're accreting from or whatever, and if the dominant factor is the square of the mass, then you actually do get this dn d log m. Actually, I miswrote this. This should be dn d log m goes like m to the minus 1, or a slope of minus 1 here. So this is gravitational accretion, and an example of this is Bondi-Hoyle accretion. So in Bondi-Hoyle accretion, there are a couple of versions of this. One version is if you're kind of plowing through a medium, and the other version is you just spherically accreting from a static gas. But basically, in this case, so you have a density and a velocity times a cross-section, pi r squared. And this r squared is the gravitational radius. And so if you stick this in, you end up with something which depends on the medium in this way. It depends on the density, of course, and it's particularly sensitive to the velocity, but you also get this m squared part. So Hans was trying to get something like an m to the minus 1, or maybe a little bit steeper for the saltpeter slope. Here, thinking about our star clusters, we could maybe apply this. You can either work for accreting gas or accreting stars. I mean, pulling stars in. But the problem is, of course, that if this is not, in general, the density and the velocity are not anywhere near constant, so how can this actually work? In particular, would there be some mass dependence on it? So we've been fiddling around with this for some time. Our first experiment was just to take a sheet of gas, self-gravitating, and just plop sink particles down. Sink particles are things that just have gravity, but they don't have any pressure, and let them accrete. So we have this nice uniform sheet. As things develop, it contracts, and you end up, by the way, with a network of filaments, which you can also see in dark matter simulations, actually, because that's gravity too. So this is the face-on view, that's the edge view, and this is things develop. And so you get some big sinks, some small sinks, whatever. And what we found was that as this went along, there actually was a bunch of sinks that got an m² slope for their accretion rate. At some point, it falls off. This is accretion rate versus mass. Here is m², m dot, the accretion rate goes as m². So you have a tail that's sort of at m², and then it kind of drops off. And what happens, what that's due to, is that basically if you've got a big guy here and a small guy right next to it, the big guy gobbles up everything, sort of like the United States economy. And so the small guys lose out, and they can't get much of anything. So there's still a tail like this, and if you then look at how the mass function varies with time, these different colors show at a different time. This is the saltpeter slope, a little bit steeper than -1. So what happens is if you have an initial distribution and you don't accrete much, then you just get back the initial distribution. But as you accrete more and more mass beyond your initial condition, then you get more and more of a power law. And ultimately, although we didn't have good statistics, you end up something close to -1. Okay? So that even though we have this complicated region with all the velocities and density fluctuations, we were still starting to approach a -1 slope. So that's kind of simple. So then let's make it a little more complicated in this paper. And so now we did something that was more like what people do when they do molecular cloud stuff. Again, we take, this was a cubic cloud, so I don't know. But anyway, put in some velocity fluctuations, they damp. So here now these are density fluctuations here, and the whole thing is collapsing under its own gravity. And then in the midst of this, sink particles get made, and you can follow the mass spectrum of those sink particles. So on the left here, then I have plotted the accretion rate, a log of the accretion rate as again a function of the log of the mass. And these are different snapshots over again. This is something that, in this case, well, I can't read it anymore, but it's the whole evolution is in 1 million years or less. So you can see the same sort of, kind of the same sort of thing that I showed you in the other plot. This is the m² behavior, and you get this turn down. In this case, the higher mass guys seem to be not quite m². Then we drop off here. But if we actually look at the mass spectra, here's how they grow with time for each of these snapshots. And at the end of this, this dashed line is the -1 slope. And so it's more complicated than just in the simple Bondi-Hoyle thing, although it sort of has this, and I can talk more about the complications that go into this. There are things about when these things form, when they run out of gas, and so on. But we do basically only gravity. We get something that is asymptotes to a -1 slope. And for several simulations, it's almost exact. I mean, it's exact as the statistics would allow us to be. So if instead of thinking of these as stars, we thought of these as clusters, and just not accreting just gas, but they could be accreting gas and stars, or turning it into stars, then we should be able to make a -1 slope. And this, of course, is potentially relevant to the upper mass spectrum of stars, right, which is the standard saltpeter slope is minus 1.3 instead of minus 1. So one might argue that, depending on whether you can evolve enough, whether the high mass stars start blowing away the gas and you have feedback and you can't keep going on to the asymptotic limit, that on average you could end up with something that's a little steeper than minus 1. But in the case of the star clusters, we're okay with minus 1. So why does this work, right? So this looks kind of funny, and of course the density and the velocities are different. So just straight, it's not clear that straight Bondi Hoyle would actually do this. What we think part of the answer to that is that there are subregions with their own characteristic density and velocity dispersions. And so that if we look at one group here, this is group 4, so down in here we've got a tight little cluster. This is, again, this is scaled, but this is the accretion rate versus the log of the mass, so this is an m squared law, so it's not perfect, but it kind of works. And then these other groups are down here, but they also extend kind of in the same direction. So, this is a very, very messy environment, so it's hard to relate it to the strict Bondi Hoyle situation. But, this is what it did. So, and basically all that's happening, because this is isothermal, they're not in magnetic fields, there's not really a whole lot of turbulence, it's just gravitational focusing. So somehow the m squared part is dominating. Okay, this, we don't need to do this. Okay, so we have these numerical results, and we're continuing to probe. Just you have other complicating things, but you'll always have gravity. So let's see what gravity does without all the other complications, and then we can add in complications and see what happens. So even though we have significant variations in the density and the velocity, so that the simple Bondi Hoyle formula, it's not clear that it works, but we still get this power law for the mass spectrum that's like minus 1. And the interpretation of this is not entirely clear. As I just showed you, it looks like there are local groups which have their own density and velocity dispersions. And so that even though their scaling is so, sorry, let me go back here. So here's the Bondi Hoyle formula. So these guys have different densities and velocity dispersions, but if each group has a spread so that they each have an m squared dependence just offset, then each group potentially can add up with the same minus 1 slope, and so then you end up getting the same. You end up getting ultimately the overall slope as a result of summing up subgroups with the same slope. As we suggested in here. Now, honestly, I'm not sure that that's the only thing that's happening, because even before you start making a sink, even before you start making a core, you start gravitationally clumping stuff, right? So if we look at this page, for example, here are density clumps which have grown. I mean, there were some perturbations, But at this stage here, you see that the perturbations were small, and now gravity's making these lumps. So it could be that there's some kind of version of Bondi-Hoyle in which basically you're setting the mass spectrum of these clumps, and then that drives the whole evolution. So I'm not sure about that, but one of the things that my student Alexandra is now doing, and we haven't finished that yet, but we should have results by the end of the summer, is that, you know, when we end up with sinks down here, where did that gas come from originally? Or another way of saying it is, do we actually see already in the mass spectrum of these clumps, do we already see the m to the -1 behavior just because of gravity? So that is something that we're still working on, but hopefully we'll have that answered. So in any case, the bottom line of what I'd like to say here is that we have clustering of stars is a natural result of having gravity. That you don't have to put in some kind of turbulent spectrum in order to get the masses of the clusters. And it looks like if we use that, not only does that work with morphology, you know, big clusters tend to be at the ends of the clouds, but we also can understand the mass spectrum of the clouds just by gravitational condensation, if you will, gravitational focusing. So I think this makes a very attractive picture. It has obvious connections, I think, to large-scale structure in the universe, where basically you're using dark matter particles and you're just using their gravity. So this is sort of my story for clustering. If we can solve this for clusters, if we can show this, then I think we will go back into the question of what sets the upper mass, initial mass function for stars, and say that, well, okay, -1 is also what the ultimately that you would get, but it maybe you don't grow to the biggest masses, and that gives you a little bit steeper slope on average, like the saltpeter slope. And if that's the case, then we have an explanation for the upper mass function, stellar initial mass function, which won't be dependent upon abundances, metallicities, et cetera, and then all we have to do is figure out what's going on at the other end of the mass function. So I think that's all I was going to say today. Thank you.
Thank you, Lee, for this nice talk. Is there any questions, comments?
I have several questions. I have for that, but okay, you are considering, for example, only gravity as the main driver of a cluster formation. All right. So, do you find some kind of connection between the highest mass cluster and the total mass of the cloud?
So we haven't really looked at that, right? I mean, there must be some relation, right? That I mean, you can't make a cluster bigger than the mass of the cloud, right? So there's that. But we haven't really, you know, actually, to be honest with you, what we originally started doing was basically the stellar mass function. And then I looked and I saw the cluster mass function. I said, oh, you know, this is even better, right? Because the clusters are so big that there are many genes masses, so you can just forget about all of that, right? And so now I'm interpreting each of our stars as a cluster, right? Which is, you know, so we need to go back and fix it up. So then I guess we could go back and see that if we did this over and over again, maybe we'd see a relation. In these simulations, to make everything simple, it's isothermal, okay? So you can rescale them to pretty much, I mean, you have to change the dimensions and change the time, but you can scale them to bigger masses. So in that case, I'm sure that if we, you know, we just follow forwardly, that it would scale directly with the mass of the cloud, what we started with. But that's not exactly what you'd like to know, right?
My other question is connected with the bonding coil accretion formula. The bonding coil accretion formula you expressed there, the V is corresponding to the velocity dispersion or to the mean velocity indicator?
Well, so there are several versions of this, right? So the way that I've written it here is for something, you know, going through the medium, right? But then there's the Bondi. So the Bondi version was you had a stationary thing, a stationary central mass, and then you had some gas of some temperature. And so in that case, this would be the sound speed, okay? But then the critical point also scales like this. So you get something with basically the same form in that for just a thermal gas accretion. So I'm saying that suppose I replace the sound speed with some velocity dispersion of objects, then maybe it would work the same way as well. So that's why I was being vague about that.
Is there any evidence of the results of the simulations for the number of zinc particles?
Sorry, say again?
Is there any change or in the results of the simulation if you change the number of zinc particles?
Well, I don't quite know how to answer that. I mean, these simulations had a couple of million SPH particles, and in each run made about 100 sinks, and then we started with different random seeds for the turbulence, and then added up all the.
So the number of zinc particles is low.
Yes. I mean, we need an absolute minimum of about 64 SPH particles to make a sink, just because of you need that for resolution, to see whether something's gravitationally bound or not. So typically, we had like 1,000 solar masses of gas, and we'd make a couple hundred sinks, so that about, at the end of the simulation, maybe a third of the mass was in the sinks. But we ran this many times, well, 4 times and added it up, because one of the problems with actually trying to demonstrate this is many simulations just don't have enough sinks to get an accurate power law slope to see what it actually is. And so you can find lots of stuff in the literature that says, well, this looks like the stellar initial mass function, which basically means it goes up and comes down.
Just to check if I understood well, when you talked about mass segregation in your simulations,
Yes.
you got, let's say, a primordial mass segregation in the sense of young big stars are together, but
Go ahead.
they would sink or infall somehow as protostars.
Well, yeah, so what happens, so there's been a long, oops, where am I going? No, it's back here. Sorry, I'm still jet lag. Where are we? Well, actually, I have a better plot, which I didn't show. Sorry. Where is it? Maybe I don't find this. Maybe I got rid of it. Okay, anyway, so it depends a lot. The problem that you have is that, so back up. So we have a couple of cases, for example, the Orion Nebula, where we know that the most massive stars are in the most clustered, okay? And that's just because of sort of an energy equipartition, right? So if if mv squared is equal, then v goes like 1 over the square root of m, right? So, but the other problem is, and of course you've got more mass there, so you think, oh, I'd like to make stars there. But you know, they can settle in pretty quickly, and so that's where the argument is, right? So these guys, there's a big lump of gas here. It's higher density, so everything's trying to fall into that part, and so these guys start growing outside of where the cluster is in this particular simulation, and then they end up there. Okay. Now, I want to say, I don't know if that's really realistic or actually how it happens in real life. I'm just saying, and that's been part of the problem of people arguing nature versus nurture. So one of the things that happens with this Bondi-Hoyle accretion or whatever is that these guys can, you know, it's not just a fixed mass that collapsed and made a big thing. It kept growing and kept growing, and so it can actually move around while it's growing, and so that makes it even harder to tell where it came from, or whether it's, you know, just looking at where it is now and what its environment is tell you that it actually grew, actually accumulated most of its mass there.
Do you have any idea on the effect of including magnetic fields on the slope of the expansion?
Well, I don't know. I mean, that's something that that's the next stage of this work, is to try and do the sync formation with some overall magnetic fields and see what happens to it. One of the things I'm sure that will happen is that we'll be more likely to make filaments, because, you know, the magnetic field, the filament will tend to form along the field lines, right? Because the field line, the magnetic field will resist it in the other direction. And so, you know, that might change the ability of you know, to be able to accrete far enough. Because now, let's see, I think I have a plot here. So as you probably know, there's a lot of argument now for low mass star formation in filaments, right? This is the big thing if it's not in clusters. So here's one of the simulations. This is the B213, and the magnetic field runs this way. You can see the striations. So that could prevent things from collapsing very well along that way. But I'm not sure that it'll make a huge difference, because what actually will happen is that these things are still accreting mass this way, right? They're not isolated things. So it could be that if you can just keep accreting mass this way, you can still grow them. But we have to do that simulation in order to see how that works or not.
So, you know, there is another approach to the problem, considering that turbulence is the driving force of the star formation. This aspect, not only gravitation, or you know, gravitation plays the second role in this question. So, do you figure out some kind of experiment in order to discriminate between these two approaches?
What was the first approach again?
You can imagine some kind of experiment in order to discriminate, or you know, these two approaches to the problem.
Well, so what has happened is that people have done a number of simulations of clouds, and they've come at it from the point of view of just pure turbulence, okay? And it's not gravitationally driven. In fact, there's a recent paper by Padoan et al. where they do this. In order to get this to work, what they do is they turn off gravity. and they let it kind of settle down with the turbulence and then turn on gravity, and then they say, okay, we can tell this, but, you know, that's a completely, well, I mean, you could do that, right? But the problem is if you never turn on gravity, you don't make any stars, so you have to turn it on at some point. You know? So there's actually been, I haven't seen it, but there's another paper where they claim that they don't need any, okay, let me back up. There is a relation between the velocity dispersion of a molecular cloud or its clump and the size scale. Okay. That is, we've now begun to realize that that's sort of like, it's basically given the velocity squared is like jam over R. Okay. So we think that particularly on a large scale, those motions are driven by gravity again. Paolo said, well, you know, we can get this without any gravity. But in fact, somebody has actually done the simulation without gravity and with gravity. And in case of making a cloud clump, you don't necessarily have to turn on gravity because you're not making a star and collapsing all the way. And they get a different result. So it does seem like, at least at the cloud core scale, that this gravitational driving of motions, at least, is important, and you have to put that in. And you can't just do it with pure turbulence. And then the problem is if you have the turbulence, but it's self-gravitating, I mean, that's what we did here, right? We basically, we put in turbulence to begin with to make these fluctuations, but we didn't keep doing it. It was just like an initial condition. The other thing about the turbulent mechanism, if you don't keep pushing it, it all dissipates and it turns into our picture. And so what they do is they keep driving it, and there's not actually any physical mechanism. I mean, they claim they can do it with supernovae, which is maybe a step forward. But if they don't turn off gravity, then they'll just, if they leave gravity on from the beginning, they get what they're doing.
I have a question. Do you think there is a general rule that works for all the regions, or that it may be possible that in some specific regions gravity dominates, and in others the magnetic field, for example, has a more relevant role? Because there are places where you see a very well ordered magnetic field at large scale, and others where everything seems to be disordered. So
yeah, I think the answer to that is yes. Let's see if I have the. So, for example, if we look at torus, all right. So this is a torus map, as you know. This is the filament that I was just showing you. This shows you the magnetic field structure, and in these regions, the magnetic field dominates. Of course, that's not where you're making any stars. So yes, you have low density regions where the field dominates, and high density regions where the gravity dominates, is what I would say. And if gravity doesn't dominate, then you can't make any stars. So there's kind of a selection effect that way, I think.
The question is the balance, the different scales.
Yes.
Now, right here, for example, we are already seeing a very well behaved magnetic field, but what happened, to the shorter scale? It's already at the same variable. We have something more, chaotic in the magnetic field behavior. So, for example, it's easier to do the stars because we have not so extreme magnetic field against the gravitation.
Right. I mean, it's a little hard to tell because we don't have very, oftentimes we don't generally have three-dimensional information to for the velocities and magnetic fields to tell just exactly how strong stuff is. So, but one thing that we have found is that there's a suggestion that you need an ambipolar diffusion in order to allow things to gravity to overcome the magnetic field, but working with Fabian Heights, we found that the easiest way of doing this fast is just to keep adding mass so that you build up the mass to flux ratio just by changing the mass, rather than having to diffuse the magnetic field.
More questions? So let's thank Lee again.
Okay,
Thank you.
I didn't fall over.
You need more coffee? You need more coffee?
No, I'm fine.